Okay, Les, thanks very much. And good evening, everyone. And it's nice to see you all here again for another online meeting of the Havering Astronomical Society. I hope everyone here this evening is keeping safe and well, both in body and mind, as this lockdown situation goes on and on. But there may well be a brighter future ahead for us if these vaccinations seem to be working out. I had mine over the weekend. Things must be looking up. This evening, as you saw, we've got presenter Dr. Dafydd Wyn Evans. He'll be talking to us about the Gaia project and the recent early data release that's come back from the ongoing project. It's been going since 2013, and although I understand it was finished in 2022, it may be going on before that, but maybe beyond that. But hopefully, Dafydd maybe update us on that. After the presentation, as Les says, I'll probably go through a few house notices and society bits and pieces, and then we'll have opportunity to have a general social chat regarding anything items astronomical. So hopefully, I'm sure you're going to find this a very interesting and informative presentation. And without further ado, I'll hand over to Dr. Wyn Evans. Thank you.
Right, I will hopefully, oops. Right, I remembered the important configuration that's needed. And my screen now, is that correct?
That's good.
Okay, excellent. Okay, so I'm going to give you a brief rundown of the Gaia mission. I'm not going to give you all the details because that would have me talking for quite a few hours. I'll be describing how the data processing was organized with an emphasis on what was done in the UK on the photometric side. The DR3, early data release 3, and I'll also be talking about describing what's going to come in the next data release, DR3. Okay, the Gaia mission is a European Space Agency astrometry mission. It was launched in 2013 on board a Soyuz frigate vehicle from Kourou in French Guiana. After the launch, there was a period of commissioning, which sorting out the sort of the first sort of problems with the telescope, etc., the initial refocusing, etc. And the official start of the data collection was in July of 2014. So we're now almost at 2,400 days into the mission. Now, on the day of the launch itself, I was, at the time of the launch, I was in the lecture theatre at the IOA in Cambridge with many of my colleagues watching the event live. And I can assure you that that was a really nerve-wracking experience. I'd been involved with the Hipparchus mission earlier, and that did not go according to plan and was not put in the right orbit. So I know what happens when a space mission goes wrong. There's a lot of depression and long faces around the place, and I was really hoping that lightning didn't strike twice. Hopefully the video can be heard by people. They really don't know how to rack up the tension with doing the countdown. I was really on the edge of the seat with this. And I can assure you that having this relayed on really loud speakers in the lecture theatre was, you could really feel the bass coming from the from this launch. So I mentioned that I was also involved with Hipparchus. This was the previous European Space Agency astrometry mission that was launched in 1989. That was aboard an Ariane launch vehicle, and that was also launched from Kourou, and was a 4-year mission. The scanning law principle was exactly the same as in Gaia, and it had 2 telescopes in exactly the same way. So Hipparchus can be regarded as a sister mission, as a precursor towards Gaia. But that's where the similarity stops. Gaia is just so much better than Hipparchus was. From the point of view of the number of sources, there are 4 orders of magnitude more sources being measured by Gaia. And in terms of the accuracy, it's at least an order of magnitude, and in some cases, 2 orders of magnitude better from the accuracy point of view. And of course, the main reason why we're getting far more sources is the fact that the faint limit is not 12th magnitude, it's 21st magnitude. And this is entirely due to the detectors that we've got on board, the difference between having a photomultiplier and using CCDs, state-of-the-art CCDs. So Gaia is now, after launch, went to L2, the second Lagrangian point in the Sun-Earth system. This is a metastable point. It's not fully stable as L5 and L4 is. So there is still some station keeping maneuvers that are needed to keep it in its location. And it's a very popular place to put astronomical satellites. Planck Herschel is there. The James Webb will be going there. And the reason why it's the place to be is because it is a very, very stable environment. You're not influenced by as much by variable gravitational fields from the Earth or from the Moon, and you do not get as many eclipse events at L2 as you would if you were in a lower Earth orbit. This is very important for something like Gaia because we want a very stable thermal environment. And if you go into eclipses all the time, it provides quite a lot of a shock to the system, and you effectively get a lot of ringing within the telescope. And if you're trying to do accurate astrometric measurements, you don't want that to happen. There is a downside to being at L2 rather than in geostationary orbit, for example. It's further away, therefore the bandwidth is less unless you put more power into the transmission. And also it needs more ground stations, or you need onboard storage, and then you squirt the data down when the ground station is in view. So Gaia is about 10 meters across. You can see the main sun shield deployed there, and underneath the sun shield are the solar panels which power the satellite. Within the main 3-meter body of the satellite, of the spacecraft itself, you've got 2 telescopes with rectangular mirrors, and this brings light onto a common focal plane, which is shown here on the right. And there are these CCDs are measuring information from 3 separate instruments. There are more than 100 CCDs on this focal plane. And one of the big publicity shots from that was used for the press releases early on was that Gaia was the billion pixel camera. So hopefully you can see my cursor. And the first part on the focal plane here is what's known as the star mapper. The star mapper are these 2 rows here, but then the main part here is the astrometric field, and this is where the main data gathering is done for measuring the positions, and the main part of the photometry for all sources. And this is effectively an imaging device. Although we don't transmit images down to the Earth, we do various binning and specific readouts from the CCDs. So it's a form of data compression for transmitting the data to the Earth. The next bit are these two strips here, which is collecting data from the blue and red photometers. These provide the color information that we need. And then the final bit here are the CCDs that gather data from the radial velocity spectrograph. Right, so as I said, there are 3 instruments on board. The main field is there are no filters there or anything like that. So therefore, the reasoning behind this is to just get as much light as possible, as many photons, to get accurate positions. But because you've then got a white light instrument, there will be chromatic effects, and therefore we need simultaneous color information in order to make these corrections. And this is provided by the blue and red photometers. These split the data, the light, into by wavelength, and that's done by these 2 prisms. And the examples down the bottom here show 7 different stars, and to show how their spectra look. And it's quite a crude spectrum, but there is a lot of information that you can get from this sort of spectrum. And the third instrument is the high resolution spectrometer, the RVS, radial velocity spectrograph. And this is splits the light using a diffraction grating, and sends it through quite a complicated set of optics. And the end result is you get a short segment of a spectrum which is centered on the calcium triplet lines, and we measure the radial velocity by looking at the Doppler shift of these lines, or of a template that's done on top of these. And you can see that there are lines that are visible here. And then from a combination of these lines and the line strengths, we can get some astrophysical results as well from these spectra. Okay. So the European Space Agency is just responsible, well, just, for the spacecraft, the launch, and the continuing operations of the satellite itself. But then it's up to the astronomical community itself to process all this data. And this is done by an organization that was set up called the Data Processing and Analysis Consortium, which we just refer to as DPAC. This is a very large pan-European organization, although there are members from outside of Europe. And this is all governed by a multilateral agreement, which is basically a contract between governments, in which the governments agree to deliver on a specific task. One of the issues that comes down is that each group within the country has to then apply for its own grant in order to do this task. And this has to be done periodically every 3 years or so. And it can be quite a bit nerve-wracking, because if there's a squeeze from the government about spending, as there almost always is, we honestly don't know whether our grants are going to be cut and that we can't do our job. We have been cut in the past, but the last grant was quite successful. So therefore, from the UK point of view, we're quite happy about that. But it is something that's quite nerve-wracking for all the teams within DPAC. Overall, there's approximately 400 people within DPAC. Not all of them are working 100% of the time on Gaia issues. Okay. So of course, with so many people, managing this amount of manpower is actually quite complex. Overall, the controlling committee is the DPAC Executive Committee, which is known as DPACE. And then each member of one of the coordination units sits on DPACE, and each one of these has a separate task. So 3 of them are mainly technical hardware, and you have CU1, 2, and 9, which are the system architecture simulations and the archive. Those are the technical ones. Then there are 3 others, which are the main upstream processing coordination units: CU3 for the astrometry, CU5 for the photometry, which I'm the leader of, and CU6, which processes radial velocities. Then we've got 3 further coordination units, which are referred to as the downstream units for variability processing. That processes mainly the epoch photometry that's coming from us in CU5, but also it does do variability analysis of the radial velocities, etc. as well. Then you've also got astrophysical parameters, CU8, which mainly takes the spectra from CU5, the BPRP spectra, and the parallaxes, and then derives astrophysical parameters from this. Things like temperature, gravity, metallicity, extinction. If we're really lucky, in some cases, we might be able to get some alpha element information from some of these spectra. And last is object processing, CU4. Its leader regards self-derogatory, regards himself as the dustbin of Gaia. Anything that we can't process in a normal manner, we just give to Dimitri, and he'll sort it out. So this includes things like the solar system objects, extended objects, and binary stars. So these all need special processing. Now, associated with these coordination units are the data processing centers, which are at the bottom, and CU5 has its own data processing center in Cambridge, DPCI. There's another one which is solely associated with one CU, which is DPCG in Geneva, which is associated with the variability process. But the rest are a bit of a mix. They help out in other over many groups, and some require help from a few data processing centers. Okay. This plot here is just to show that it's a tangled web of stuff. You don't have to understand the various anachronisms or acronyms and jargon that's in this plot. The data that we're getting is very complex and challenging, and one of the main reasons is the interconnectivity of this data. So the astrometry needs the colors that's coming from the photometry in order to do its job properly. But the photometry also needs the astrometry because it provides the attitude and the geometry of the CCDs. So without that, we won't be able to know where the wavelengths are for the BPRP spectra. So you can't solve for this all simultaneously. So we have to process this cyclically. And another issue is just the huge quantity of data. I was at a meeting today and somebody was bandying about however many trillion windows he had to process. It is a really large, it is part of what they call big data. And of course, from this plot, you can also see that photometry is central to all of Gaia processing. Yeah. So all this processing has to be done on a quite large computing cluster. This is hosted in the West Cambridge Computing Centre. We've got over 200 nodes, which does all the processing and the storage for us. And there's quite a lot of heat generated from these computers. So simple fan-based, air-based cooling system is not enough. So that's what these huge pipes are going into these computer racks. This is a water-based cooling system. So you've got cold water coming in one end and warm water coming out the other end. So each node has got 12 cores, an associated number of disks, and of course there's quite a powerful and fast network that connects all of this together in order to do the processing in an efficient manner. So overall, we've got more than 5,000 cores, about 60 terabytes of memory, and just under 3 petabytes of disk storage on this part of the cluster. But we've also got, in addition to that, we've also got a 1.6 petabyte RAID storage array, and other servers that are handling things like the data deliveries to and from Cambridge, various data analysis, things like the various validation processes that go on, the handling of science alerts, which I'm not even going to describe at all, but that's another important part of the work that's done at Cambridge. And as I said, the majority of this is all hosted in the West Cambridge Data Centre. Okay, so the main thing that Gaia measures is the astrometry. And the three components of the astrometry is the positions, the proper motion, parallax. And you can see this, that if you plot the position of a star as a function of time, which is shown in these three plots here, you can see that you get this sort of either spiral structure or a cuspy structure. And the overall motion of the star along here gives you its proper motion. And the annual motion here, either a spiral or this cusp structure here, is determined by the parallax, and then from measuring this you get the parallax of the object. Now, in addition to these three things here, we will also be getting, for some stars, we be able to get the orbital motions of some of these stars, because some of them will be in binary systems. So on top of this stuff here, you will get very small wiggles, and from that we can measure the binary motions of these stars, and sometimes maybe even of planets going around these stars. Of course, in addition to the astrometry, we've got photometry. So we've got the main G magnitude, which is the white light magnitude, and we've also got what are called the BP minus RP colors. And this is simply, the most simple measurement of the colors is that we're treating the data from the spectra from the prisms as photon buckets, and we then just calibrate that to give us our colors. However, we are dealing with the low resolution spectra more accurately, and the calibrating of that is quite complicated. So we've also got the radial velocities. Now, in terms of the positions and velocity of a star, that's in 3 dimensions. You've got 3 dimensions for the position and 3 dimensions for the velocity. The astrometry can only give you 5 of these overall dimensions. And in order to get the 6th dimension, you require an additional methodology, which comes from the radial velocities. But the telescope isn't really powerful enough to measure everything, measure the radial velocity for everything. So we're only going to get radial velocities for the brightest sources in the catalogue, down to probably about 16th magnitude. Now, additionally, we're doing the variable analysis, which mainly uses the photometry, and also the astrophysical parameters. And the reason that we're doing it within the project is that this is critical to the validation of our data. If we can see some problems in the analysis of the sort of the science analysis of this information, we can then say there's probably something wrong with the source data, and then that can then guide us to actually fix this before the data is actually released. So these two aspects are critical to our work. So when we're releasing the data, we've released it in sequentially as a gradual release, and as the data becomes available. So in 2016, we had our first data release, which was only positions and magnitudes. We did have a few parallaxes, but it was only at the bright end. And the reason we didn't have parallaxes and proper motions was the fact that we only had 14 months worth of data. That wasn't enough to disentangle the information. But also with only 14 months of data, you can see that there's quite a lot of, in this image here, of in galactic coordinates. So you can see the plane there and the large and small Magellanic clouds here. You can see that there are quite a lot of obvious features that are coming from our data processing, the various grid lines and sort of scratch marks. Now, in 2018, we then released DR2, and that was a huge improvement. This then meant that we had parallaxes for most sources, and we also were adding color information to all the data. And the reason that we had the parallaxes was the fact that we had 22 months worth of data rather than 14. Then last December, we had our the next data release, early data release 3. This had an extra year worth of data, and this meant that the parallaxes were 30% more accurate, and the proper motions were almost a factor of 2, well, more than a factor of 2 better. And this is what this representation on the plot shows here as one of the publicity shots that we used. This shows effectively the reflex solar motion of the direction of where the sun is going with respect to the rest of the galaxy. And of course, in the intervening 2 years since DR2, we've had more time to analyze the data, so more systematic errors were corrected. So the total number was about 1.8 billion sources, and about 1.5 billion contained parallax and proper motions. So the 5-parameter and 6-parameter astrometry contains that sort of information. And also it's very similar figures for the main white light photometry that was coming from the satellite. So for that, and then the color information is 1.5 billion. We also re-released the radial velocity data, mainly as a convenience for astronomers. There was also a few corrections that was done to the data. It's not as large as the rest of the data release, but it's still very significant in terms of comparisons with other catalogues. It's by far and away the largest radial velocity catalogue that's been published. Now, the thing with EDR3 was the fact that it had fewer systematic features and that there was a progressive improvement in the calibration accuracies. So the main thing that you get from this plot and the next slide is that I'm showing here the performance as a function of magnitude, and the lower the line gets, the better the thing is. So the main thing to compare with is the blue and the green lines. So this is the one for DR2 and EDR3, the current data release. And then the yellow and red gives the future data releases that are planned. And you can see that we've improved things, in particular at the bright end between 6th and 13th magnitude. There's quite a step change, which reflects that we've got the calibration sorted out better. But if you look at the proper motions in comparison to the parallax, the jumps are much larger, it's a much more of an improvement. And the reason for this is the fact that not only do you get more data from this data release, and that improves the statistics, you also have a longer baseline, which means that you can measure the proper motions more accurately. So from the photometry, you don't have that baseline effect. You only have the effect of calibrating or getting hold of more data. But in these specific plots, we have actually already accounted for the amount of data that's coming in. So the only thing that these plots are showing are the improvements that have been done in terms of the calibrations. So for the very first data release on the top, the very light green line, there were quite a lot of features that were obviously not to do with astrophysics or the expected statistical analysis. And very pleasingly, from my point of view, as the data releases are going out, we're reducing the systematic effects. And the recent work I've done a couple of weeks ago should get rid of these two bumps here at 11th and 10th magnitude. So we're getting down to the theoretical limit of what we should be able to achieve. Okay, and another way that you can look at how good the data is to plot various features as a function of sky position. So the top two plots is showing the average color of the sources in a particular part of the sky. In this particular plot, it's towards the direction of the galactic bulge. And on the left is the results from DR2, and you can see this sort of quilting pattern or weave pattern, which comes from our scanning law. And it's obviously not a real effect on not quite right with the data there. And if you then look at EDR3, the latest data release, it's a lot smoother. And what the effects that you're seeing there, that's real astrophysics. Different colors from various clumps of stars. So the bottom plots are showing a sky plot in galactic coordinates. And for the DR2 plot, apart from the main galactic plane here and the imaginary clouds, the thing to notice here is this line here. This is directly on the ecliptic plane and is an effect known showing the effect of zodiacal light. So this is sunlight that's reflected in dust within the plane of the solar system. And this causes problems for our background corrections. And we obviously in DR2 didn't get it perfect. So when you then go over to DR3 here, you don't see any of that S-shaped systematic. We've also had the crowded regions a lot better, but there are some effects that we can't get rid of. And you can see still some remnants of the scanning laws, which are some of the little wispy patterns that you can see there. Okay. So on to some of the science bits that are coming from that came from DR2 and from EDR3. There have been so many papers published using Gaia data. I can't begin to summarize this. So what I'm showing here is very personal selection of what excites me about various bits of the Gaia data. So one of the things that Gaia is very good at doing is producing HR diagrams, Hertzsprung-Russell diagrams. And this combines magnitudes, distances, which you get from parallax, and color. You combine them together, and in this plot here, this gives an intrinsic property of the star itself, and it's not dependent on how far the star is away from us. And from this, you can identify what sort of star you've got. So if a star lies on this sort of locus, it's a main sequence star. Here you've got the red giant stars, and you can then see further detail. You can see the red clump here. You've also got a second locus coming slightly above the main sequence, about 3/4 of a magnitude above, and that comes from binary stars. You've also got more stars here, which come from binary stars, but this is binary rather than binary main sequence binaries. This is from main sequence and white dwarf binaries. And then over here, you've got the white dwarfs. So those of you that are eagle-eyed may be able to see that you can actually see two ridges on this white dwarf sequence. And also, you can see maybe just this very faint sort of smidge here. And this is, I'll describe that in a little bit detail later on. Okay, so first onto the white dwarfs. When I saw this, this really blew my mind away. I have never seen so much detail in a white dwarf sequence before. Normally you just see a single line because the errors on both the photometry and on the astrometry from the parallaxes, it smears everything out. But here you can see a clear separation between the two main sorts of white dwarfs, DA and DB white dwarfs. These are the hydrogen and the helium burning white dwarfs. You've also got about 3/4 of a magnitude above here, you've got the white dwarf binaries. And then there really is an overdensity here, a significant overdensity. And this comes from DQ white dwarfs. These are white dwarfs with carbon in their atmospheres. And that's the first time I've seen a sequence which involves DQ white dwarfs. So this feature that was seen in the lower main sequence, I got a lot of stick for this, because whenever an astronomer sees a diagram with a feature like this, they say, oh, that's just a systematic effect. That's a problem with the data processing in some way. You obviously can't get some real effect that displays something like this little glitch, which is a very narrow glitch around 0.05 magnitudes. And what everyone is asking is this a problem with the data, or is it a real feature? And the analysis was done by Zhao in 2018, and the effect is real. It's also seen in the near infrared, and it occurs around where M3 dwarfs would be in the main sequence, and it's linked to the onset of occurring within the M dwarfs. So it is a real astrophysical effect. And when I processed the or got the first results from the latest from the data that was going to go into DR3, one of the first things I did was to plot a HR diagram and look at this region to make sure that the gap was still there. Because if the gap had miraculously disappeared, it obviously had been a problem in DR2 and would have been egg on our faces. But this is real, a real science result that was, which looks like it's some form of glitch in the data. Now, although I'm the leader of the photometric processing, I'm also the deputy manager of the variability group. And I'm very interested in these because they are one of our first customers, effectively, of the photometry. And in going from the first to the third data releases, we are progressively releasing more and more variable stars, light curves from these stars. And so the first one had 3,000 RR Lyraean Cepheids, and then the DR2 had 500,000 and included many more variability types. And in DR3, we're intending to publish around 7 million variables and many, many more different. And the plots here are showing some of the folded light curves showing the periodic nature of the RR Lyraean, the Cepheids. And the really significant thing about Gaia is that it's measuring in 3 different passbands simultaneously, or near simultaneously. So you've got light curves coming in from the white light plus the BP and the RP. And effectively, the different heights of these, in particular, you can see it in the bottom one here. You've got a difference of 3 magnitudes here from peak to peak, and it's only about 1 magnitude for G and R. And it therefore shows that the color of these sources is also varying in addition to the magnitude. Now, of course, Cepheid variables are very important because they provide the first rung on the cosmic distance ladder. And this is because the brightness of the Cepheid is intrinsically related to the period of the Cepheid. So you can calibrate this by measuring Cepheids that you've got a good parallax measurement, a good distance measurement to. And then from that, you can then go to more distant objects, which are not being observed by Gaia, like, for example, something that's an extra a galaxy that's being observed by, say, the Space Telescope. And it measures variables in these galaxies. And from measuring the period of these variables, you can then know how intrinsically bright it is. And from comparing that with the measured brightness, you can get a distance to these. So then you're extending the ladder from what we can measure directly from parallax to something that's measured from these Cepheids. So Gaia measuring the parallaxes of these variables is very important from a cosmological point of view. Okay, so the Magellanic Clouds are 2 of our galaxy's nearest neighbors. They are satellite galaxies of ours, and because they are so dense, we can get much more bridged information and can analyze the data a lot better in these regions. And this can show systematic effects and problems with the data much more than we can in the general field of the galaxy, of the sky. And what you see on the left-hand side is what happened in DR2. And you can see this sort of bobbly pattern around the central parts here. So around here and here. And this showed that there was an issue with the data processing in DR2. But now we go over to DR3, which is the plot on the right-hand side, and you can see that you can't see any of this quilting pattern, which was a remnant from the scanning law. So we have made significant improvements. Now, in addition to that, we can actually look at the real data. So that was just a diagnostic plot of these regions. Now, these plots are showing the densities of the stars within the LMC and the SMC. And these are very pretty in themselves and sort of show the structure of these satellite galaxies. You can see the central bar of the LMC quite clearly. But what I find absolutely amazing is that using the Gaia data, you can actually measure the averaged proper motions within these galaxies. And you can actually see the effect of rotation within, in particular, the LMC. Now, when I was doing my PhD, we were trying to measure just the single measurement single proper motion measurement of the whole of the LMC. And we knew that we couldn't do it because of the fact of systematic errors. But we've now got to the stage with Gaia in that we're actually measuring the velocity field within this galaxy. And it's very nice that you can actually, I like it so much, I'm going to show it again. You fade it in and you can actually see the spiral structure, the rotation that's occurring within the LMC. And then you compare it with the SMC, which is much more regular. Now, the eagle-eyed of you will have noticed this little dark blob here, and that's where the large globular cluster 47 Tuc lies. And due to the way that the filters were working, or the sort of the computing filters that we applied to the data, that data has been removed from this analysis. But I really like this plot. This again blows my mind, that you can actually see the individual movement of stars within these galaxies, which are outside our galaxy. Okay, so what's going to happen in DR3? So that will occur in the middle of next year, and we'll release the same data that we've currently got in order to have it all in the same catalogue. There will be some corrections to the data, but the data will essentially be the same. But we'll also have many more radial velocities than we had in the second data release. We still don't know how many more, but it will be a lot more, an order of magnitude probably. And it depends on the data quality. And then we'll also have mean spectra from the RVS so that people can analyze further. We'll also have astrometry for solar system asteroids for 100,000 of these. And in addition to that, we will have mean reflectance spectra for 5,000 of these objects. Now, these are spectra of these objects that have had effectively the solar spectrum subtracted out of them. So it's sort of giving you a spectral albedo for these. So you then can work out for these asteroids what they're made of, because different minerals have different reflective properties. As I said, we'll also have 7 million light curves from the photometry. But one of the main things will be that we will be releasing the first tranche of the BP and RP mean spectra. And this is going to be probably more than 100 million. And this will be the largest spectral catalogue that's ever been released. And tied to this will be the astrophysical parameters that are derived from these spectra. Additionally, we will release the Gaia Andromeda photometric survey. This will be the light curves of all sources within 5.5 degrees of M31. This is in comparison with the general photometric light curve release, which is we first identify them as being variables. So this will release the data for constant stars as well. So people can check to see what's happening with the data, and it'll give a taste of what's going to be released in the fourth data release. So prepare astronomers for what will be available then. But as I was saying, the main thing from my point of view is that we will be releasing these 100 million plus spectra. And from this, you'll be able to generate synthetic photometry and derive various astrophysical parameters for each of these stars. So I hope I've persuaded you that Gaia is totally awesome. When DR2 came out, an American astronomer was being interviewed on CNN, and she said that today was the most important day in astronomy ever. I just wish that we had someone like that to work on our publicity. She really was selling Gaia to the Americans. And Gaia itself is representing a paradigm shift in astronomy. We are changing now from observing individual objects with a telescope to doing data mining. So from now on, you're observing the catalogue. There is so much information in there. You're not going to be able to analyze it by yourself in your own lifetime. Everyone can look at their own individual fields and find data that's going to be useful for them. And of course, the other thing that's fantastic about Gaia is the fact that the data is free for everyone. As soon as we've processed the data and feel that it's calibrated well enough, we release it. There is no proprietary period for it. And this blows the minds of the Americans, because they're used to having data that their university has paid for building the telescope. Therefore, they've got 1 or 2 years free use of the data before anyone else gets their hands on it. So when the data came out, quite often there would be these things called the Gaia sprints, in which were parties at 6 o'clock in the morning, in which people were huddled over their computers. They'd already sort of pre-written the paper. They had an expectation of what the results might be like. They'd pre-written the papers, and they had their data scripts ready. They downloaded the data, they run it, and then they inserted the data into the paper. And the only thing they had left to do then was to write the conclusions. So this is why you would then get papers coming 3 days after the release. No, less than that. There were some papers coming out a day after the release of the Gaia catalogue. And this also doesn't stop any of you out there to have a look at the Gaia, the catalogue. The link is there. I think you have to register, but that's all. So if you want to analyze your favorite patch of sky, feel free, go ahead and do it. You don't have to be a professional astronomer to look at this data. And that's what it's there for everyone to use. And I think that's it. Thank you very much. So any questions?
Just switching the video back on. Dafydd, absolutely fascinating talk. Thank you very much for taking us through that, and indeed your sort of experience of the data sets as well as the organisation, which is always intriguing.
Well, I thought that rather than going into too much detail of the science, that, you know, I'm sure that some of you out there are involved in management and the likes, and sort of this is now what it's come to. It's not academic poring over a telescope and writing a paper. It's now very large groups analyzing the data with big computers and producing very large catalogs.
Indeed.
I'm keeping on sharing, if that's okay, because if there are any questions, I might want to go back to the slides.
What I was going to say is, before we move to the Q&A section, perhaps we can all thank Dafydd in our normal way. I think everybody should be unmuted. If you're not, please do so. And thanks very much for a great talk.
Very much. You're most welcome.
It's about as interactive engagement we can have with a live audience.
Yes.
These days. Now we have had quite a few questions coming in, which is excellent because it shows the engagement. So let's go right.
It's so complex that you don't understand what I'm talking about.
Yeah, well, I mean, the first question, I mean, they're obviously inevitably in talks of this nature, there's a little bit of jargon and
Yes.
and so on. And one of our members asked a question, what's a CCD? Well, sort of answered, but perhaps you could sort of elaborate a little bit on perhaps on the sensors that you're using. And
CCD is a charge coupled device. Effectively, it's a camera, or a detector for a camera. You've got a CCD in your mobile phone. You've got a CCD in your camera. This is a light-sensitive detector that converts photons into information that we can then read out. On your camera, it produces a nice, pretty picture for you. On a telescope, it can also produce a picture, but from our point of view, it produces data for us. Hopefully that's answered enough. I don't know whether I need to do more.
No, that's fine. There was a question that came in towards the end, which was about the technology and how that sort of developed. Presumably, it was state of the art back in sort of 2013 or the early part of the decade. Where are we now, as it were? Let me just jump to that question because it is sort of related. Are there any other unexpected developments or innovations in data processing technology in the last 7 years since that have subsequently improved the process?
Well, we are still, since we're processing now, we are still using advances in data processing as we're going along. With respect to the detectors, yes, we are. There will be new detectors going out. In particular, for example, James Webb will be using infrared detectors. They're not CCDs, but they're the equivalent of CCDs. So that's a big difference. And I'm not well up on this, but I would expect that the data rates would be more efficient for transmitting data down. Of course, the James Webb is a much bigger telescope. One of the main things with the European Space Agency is that you will only get funding for a satellite unless it will only get it if you have got something that drives the technology. So with Gaia, the main thing there was with the silicon carbide infrastructure and the mirrors. So they developed this new technology in order for us to have the satellite. And the European Space Agency wouldn't have funded us unless we had that technology driver associated with the project.
Interesting. Sort of linked, how much processing, if any, is actually done on Gaia before it's sort of squirted down to the ground?
There's quite a bit of simple processing that's done. First of all, you have to, I haven't explained how the satellite works, but the first detection gets done by these CCDs, and some form of processing has to be done to work out where the star is on the field and how bright it is. And then this determines how the configuration of the satellite works later on. And we convert two-dimensional images into effectively one-dimensional images. And this then is the data that's squirted down. So a form of data compression gets done before being sent to us. And that's effectively the main amount of processing that's done on board.
Okay, so really to help the data transmission, I guess.
Yes,
as anything.
Absolutely.
Yeah. Okay. Question on if Planet X exists, would the data from Gaia help to locate it or prove that there's not another planet in our solar system?
I'm not sure. The reason I'm not sure is that the sort of planets that would be affected by Planet X would be very far away and therefore very faint, maybe beyond the capacity of Gaia. Not entirely sure. No, we do measure Pluto and Charon. I think that there's a possibility that that would be the case. I remember one of the things from the main proposal for Gaia when it first came out was that it said that the measurements for the asteroids that were done by Gaia would obviate any ground-based measurements for 100 years. That any observations that were done on the ground for improving the orbits would be obsolete. They wouldn't provide a significant contribution until you've got 100 years in the future. By then the measurements of Gaia would have degraded by because of errors. So I think from the accuracy point of view, we could well detect something or prove the absence, which is more difficult. However, it may well be that you require something that's a little bit too faint for Gaia.
Okay, great, thank you. Will the data give us a picture of how our galaxy looks if we could have a bird's eye view?
Not really. The reason being is that although we are measuring towards, we can measure stars that are at the galactic center, but the thing is that's only the brightest stars we can see at the galactic center. So we can get a local view, but we can't get like a bird's eye view. To be honest, we're getting prettier pictures using artists for that, so that's fine.
Excellent. And oh yeah, comment in terms of the scaling. You showed a couple of charts, but what's the distance limit for parallax now with the latest release?
It's tiny.
Well, it depends really on how accurate you want the parallax, whether you want it at 10% accuracy or 1%. We should be able to get, I think, 10% accuracy down to the galactic center. So it is providing, 1 to 2 orders of magnitude better than we've currently got from Hipparchus, and we've got far more sources. We will be measuring. I got a radio interview. I think we'll be measuring. I said 10%. I was wrong by an order of magnitude. We'll be measuring 1% of the content of the galaxy. So it depends on the magnitudes of the stars, of course, as to how far we're going. We'll get the local neighborhood really well. I think there's a paper out on the nearest the stars within the 100 parsecs.
Okay. Great, thank you. So a couple of questions on binaries. How many new binary stars have been found? And is there any data on white dwarfs orbiting potential black holes?
Okay, I don't know exact figures about binaries. You'd have to. I think there's some work on that in the various data releases in the.
There is a flag for it.
Yeah, in the documentation. The main stuff that's coming from the analysis of binaries will be coming in the next data release, I think. But the white dwarfs around black holes.
Or perhaps feeding.
It's not.
Feeding others.
It's not the white dwarfs around black holes, but there will be. We think that we can get the detections of stars, ellipsoidal stars. Basically, the tips, the stars are basically distorted by the presence of a nearby black hole, and this comes from the radial velocity measurement, and from the simple sinusoidal measurements that we would expect can show the evidence of a black hole being present as part of the binary. This is actually quite fresh information. It hasn't been published yet, but the analysis, I was actually discussing this with a group in one of my interminable meetings this afternoon. And it's only within the last year that they've started putting forward this proposal as part of the variability analysis that they think they can do this. I think the project was called something like BEERS or something. The B stood for black hole or something, but they wanted to get a cool acronym for it. But so there will be a paper on methodology coming out pretty shortly about this, probably for next year.
Excellent. Okay. Are you okay for another?
No problem. I'm not going anywhere.
I was just thinking about your tummy rumbling.
Not yet. I've got it pre-prepared. So
Okay, excellent. Will there be a fourth data release in due course?
yes. There'll be a fourth data release and a fifth. The fourth data release has a misnomer of being known as the final data release. It's not the final one. The fifth one will be the real one, but it's the one that comes at the end of the nominal mission, the one that comes after the 5 years mission. What I haven't mentioned is that the nominal mission was scheduled for 5 years of observations, but we've got the satellite was working so well, and we over budgeted for the cold gas, which controls the station keeping and the how the satellite spins. We worked out that we could run it for another 5 years, and the European Space has given indicative approval for us to do so. In fact, the latest information says it's even pushing it slightly beyond 5 years, which may give us funding problems from the data processing point of view. But it's a good position to be in. So the data that comes from 5 years, that will be released in data release 4, and I can't really say when that will come out. This will then, we've actually collected all the data from the 5 years of the mission, and everything will then be published. So all the epoch data, all the spectra will be published, and about 5 and a bit years after that, we will then release data release 5, which will be the additional 5 years. So the full 10 and a bit year mission data will be analyzed. And the thing is that what happens then, not only will we get parallaxes and motions, we'll be getting acceleration components and much more detail of planets going around other stars and binaries. So the 10-year mission has got a lot of different science that's coming in.
Excellent. That sounds like an expanding brief.
Oh, yes.
Yeah.
It keeps me to my retirement, at least.
Excellent. Okay. How many, this is an intriguing one. How many galaxies have been eaten up by the Milky Way, according to the latest data?
At least 2 that I know of. There is, well, big events. There's well, eaten up is passed through, come out, eaten and spat out. So Sagittarius is one, and there's the other one which is called, either, depending on who you talk to, it's either called Enceladus or the Sausage Galaxy. So that one was, I honestly can't remember. I think, yeah, I'm not going to give you data the information that I vaguely remember, but there's quite a significant difference from these two in terms of time between these two events. Mm-hmm. And Gaia has shown that there are at least 2 big events that have occurred, and this helps the formation. Well, this has caused the formation of things like the thick disk of the galaxy. So as a galaxy goes through the main disk, it perturbs it such that it then puffs it up and forms a thicker disk than the thin disk, which is formed from the gas itself that is still remaining in a sort of thin disk within the galaxy. Some of the passage of these galaxies through our main disk you can see as galactic streams. There are quite a few of the galactic streams, so therefore that shows evidence of maybe other galaxies going through, being eaten by it, or it may be remnants of Sagittarius going through many times through the galactic plane. Wow.
Excellent.
Being in the galaxy, we might be hit by another one.
Yeah. Well, I guess we've got that event to come in about 4.5 billion years' time, haven't we? With our
something like that.
M31.
Yeah.
Okay. Do we know what format? And I guess this is a loaded question, John, because of your interest in this.
Not meant to be loaded, but kind of curious because I've been playing with some of the other data from Gaia. So
okay,
I'm curious what's going to happen here.
Yeah, the data for the photometric spectra will take when published in the archive for DR3.
Okay. This is going to be quite a technical question.
Sorry.
That's all right. The way that we measure the mean spectra is using basis functions rather than sampled spectra. So you're not going to get it in terms of this is the light level at this particular wavelength. It's going to come out as a continuous function. So you've got coefficients in front of each of these basis functions, and you've got to generate your own, effectively, you generate your own sampled spectra. Now, what we have done for your convenience is we have written a Python application called Gaia XPy, which you feed the data in that you've extracted from the archive, and it will then generate, not only will it generate the sample spectrum at whatever sampling you want, but it will also, if you've got, it's also already got some passbands within it, it will also generate synthetic photometry for you.
Okay, that's cool.
There will be some sampled spectra within the archive in DR3, but this will have been generated from Gaia XPy anyway.
Yeah.
We are really trying to push people to using the continuous representation rather than using sample data, because if you use sample data, you're losing information.
Yeah, okay. Cool. Well, thanks. That's a good answer. Thank you.
Great. Thanks for that, David. Two more questions, and then I think we'll draw a line. Just in respect of your time. To what purpose will Gaia be put to after the 5th data release? I think you were hinting at some things earlier.
Wait, sorry, do you mean what will the satellite be used for? Well,
that's the question.
It just dies. It will run out of cold gas, which is the way that it controls its spin. It won't be able to spin properly. It will also then move away from the L2 position due to perturbations from the moon and the like, and it'll be lost in space, presumably. So that's it. You know, in the same way that Hipparchus was effectively switched off, still going around there. There's no plans for decommissioning or anything like that. It's far too far away, but you know, it'll die a quiet death.
Fondly remembered.
Yes, exactly.
And our final question, when will we get to see a revised HR diagram?
Well, you could make your own.
Yeah.
Yeah, you can put whatever filters you want to. I don't think there was a specific HR diagram with this data release in terms of a new one published, like an official one, because every analysis that you do will have a different requirement. There is a paper with this data release on the nearby neighborhood. I believe there's a HR diagram in that. That was a paper by Ricky Smart et al. If you want to do your own, I would recommend that you have a look at the paper that Karine Babissier wrote for DR2, and then see what sort of filters she used, and then use the same filters and use it on the EDR3 data yourself. So basically, the data is all out there. You know, the world is your oyster. The galaxy is your oyster.
I think there's a sample.
Thank you.
I think there's a sample query for it on the Gaia tutorial.
Ah, okay, that's good. Excellent.
Perfect. Thank you.
And also that gives you an idea of how to learn how to, you know, there's a programming language called ADQL for extracting data from the database. These can get very, very complicated.
If you're comfortable with SQL, they're not too bad.
It's very similar. It's very similar to SQL. It's just got a few more bells and whistles that are astronomy related to it. So.
Oh, brilliant. Thank you. Thanks for answering that.
No problem.
Great. Well, I think we've come to the end of our questions. There may be sort of more that bubble up, but for the time being,
I'm going to go off and have my supper.
yes.
If you have got any more questions, just email them to me and I'll email a response. No problem.
Perfect. And just to manage that, if folk have got questions, you can either fire those over to myself or to Peter Morris, because we've got Dafydd's email, so we can get those over to him. That's very generous of you. And once again, may we just sort of thank you for your time and such an interesting talk. So thanks very much.
And of course, I can stop sharing now. You can have your screens back now.
Brilliant.
Okay, nice to have met you all, and enjoy the rest of the evening.
Thank you, Dafydd.
Thank you.
Very much.
Thank you.
Right, bye.
Bye.
Bye-bye.
Bye.
Bye-bye.